Welcome to our very last a MyLab example video. This is section 11.6 optimization. So let's get to it. All right, so for this problem, we have a quantity, the product of two numbers, x and y, whose sum is 19. So we have x plus, or x times, right? Product means you're multiplying. And we want to know this as f of x, so that means I want it all in terms of x, so I have to do something with that y. But we also know that their sum, so that's adding the two, is 19. So if I want to get rid of this y over here, all I do is use my sum, some quantity that I do know, and solve for y. So y is equal to 19 minus x. And so my f of x is equal to x, and then I substitute my y in. So 19 minus x. And if you want, you can simplify as 19x minus x squared. But either of these two answers are fine. Right. Now we have a rectangle. It has a length of x and a width of y. We know that its area is 209 square meters, and the area of a rectangle is x times y. So we know that x times y is 209. And we want f to be our perimeter of our rectangle here. And so our perimeter is this whole distance here, plus this distance, plus this distance, plus this distance. So let's say we were putting a fence around our house, then perimeter is the amount of material that it will take to build a little fence around this rectangle. So we have an x over here, so we can just do x plus y plus x plus y, which we can also write as 2x plus 2y. So this is our f, but we want this all in terms of one variable x. So like we did in the last problem, I'm going to solve for y, so I can get rid of this y in our f. So y will be equal to 209 over x, or that we can plug this in now. So 2x plus 2 times 209 over x. So you can write f of x now like that, or you can simplify it just a little to be 418 over x. All right, so now let's take that one step further and see, we're gonna bring in the notion of optimization, which means we're either maximizing or minimizing some quantity. So it's kind of similar where we have two numbers whose sum is 15, so we can make these two numbers x and y just as variables, and we want to maximize their product, so x times y. All right, so in order to maximize it, I need this function right here, we can call it f. I need it in terms of one variable, let's say f of x. This is kind of similar, or at least related to what we just did. So let me solve for y using our known equation over here, that y is equal to 15 minus x. So let me plug that in, and I get 15x minus x squared if I distribute that x through. Right, so now we have this function. It's kind of like a parabola, upside down parabola. Kind of makes sense because we want a maximum. So we want to know, where is this a maximum and what numbers make it a maximum. All right, so kind of looking back to 11.5, when we were talking about maxima, we used the first derivative. All right, and this allowed us to find potential points that were mins and maxes. So we take the derivative, we get 15 minus 2x. And so now I want critical points. And if you recall, critical points are my derivative is not defined or when my derivative is 0. So because my derivative is a line, it will be never not defined. But my derivative can equal 0, and we can solve for that by solving for this equation. So 2x equals 15. So when x is equal to 15 over 2. So now that we have this critical point, we have to ensure that it is a maximum for our function f. So how we were doing sign charts and all that good stuff in curve sketching, I believe, we're gonna plug in some test points and see what the signs are. So 15 and a half, that's like 7.5. So let's test 0 and 8 perhaps. So let's plug that into our derivative. F prime of 0 is equal to 15 minus 2 times 0. So this is a positive number, right? Positive 15. And f prime of 8, if we plug in 8, I get negative 1, so we get a negative number. And so this means that my function is increasing before 15 halves and then it decreases. So 15 halves will be a maximum. Right, so x equals 15 over 2 is one of my numbers, but let's recall what the question's asking for. We want the two numbers. So we have to revisit this equation or relationship between x and y to solve for what y is again. So 15 minus, plug in what I just found for x, and so this gives me 30 over 2 minus 15 over 2, which is also 15 over 2. And this is y. This is our second number. So the maximum actually happens when they are the same and 1/2 of 15. So 15 halves, comma 15 halves is our answer for this one. Right. Something similar, but now we have a difference of 16. So x minus y is 16. And we want to minimize product now. Minimize product. So our f is now this x times y. But again, I want that all in terms of x's. You could also get it all in terms of y if you suppose it doesn't really matter. But you want it in terms of one variable, basically. So I get x minus 16 and then move the y to the other side. Y is equal to x minus 16. So let's plug that in for y. And then I'm going to distribute that x in. That's what I got for my f in terms of x. So now let's take the derivative and get 2x minus 16. So again, now we want critical points, so not defined or 0. Again, this is a line, so we won't have any points where my derivative is not defined. But we can solve for where my derivative is 0, so that's where 2x is equal to 16 or x equals 8. And so now we have to check that 8 is a minimum now, right? We want a minimum. So let's plug in the test points 0 and 9 into our first derivative. Prime of 0 is equal to 2 times 0 minus 16, so that will be a negative number. And then f prime of 9, plug that in, and so that's going to be 18 minus 16, which will give me positive 2. All right, so my function will look something like this at around 8, so it is a local minimum. Now, there's another technique called the second derivative test that I believe MyLab walks you through, like if you do show an example. So instead of doing this sign analysis, you could alternatively, and this is to check if x equals 8 is a minimum. Alternatively, you can find the second derivative of x, so that's here, right, the derivative of f prime, And so this will just be 2. And if my second derivative is positive, then that means that, or positive at 8, let's say, or whatever critical point, if it's positive, then x equals 8 is a minimum, a local min. If my second derivative were negative at that point, then x equals 8 is a local maximum. Okay, so it's kind of opposite, counterintuitive. And then the last one, if my second derivative is equal to 0, then the second derivative test, that's what this is called, is inconclusive. So then that means that you have to go back and use the first derivative test. That's what this is called, first derivative test. Okay, so that's why I kind of like using the first derivative test straight off the bat, just because you don't have to find the second derivative and you don't have to run the risk of the second derivative test being inconclusive. But if you like finding the second derivative and using this kind of logic below instead, go for it. But just keep in mind that you may get the case where it's inconclusive. All right, so we got x equals 8 as one of our numbers, but again, let's remember what we have to answer. So we want the 2 numbers. So I'm just going to plug in 8 into this relationship. So 8 minus 16, and now find y to be negative 8. So the 2 numbers are negative 8 and 8. Okay. So now we have a rectangle, so let's revisit our rectangle. And you can use whatever variables you like, length and width, or x and y, however you want to label it, it doesn't really matter. I'm just going to stick with x's and y's. But anyway, we know the dimensions has an area of 256 square feet. And the area of a rectangle is x times y, right? And we want to minimize perimeter, where we did a perimeter problem a little earlier, where our perimeter is 2 x's, so that's this x plus this x, plus 2 y's, so that's this y plus that y. All right. In order to minimize it, I'm going to take the derivative, but that means that my p has to be in terms of one variable. So I'm going to solve for y using our area equation, and then substitute that in wherever I see a y in perimeter. So 256, like so. And so 2x plus 512. And then I'm going to bring that x up to the numerator and make the power negative, because this will be good. I'm sorry, this is not the derivative. This is just p. This will be helpful for our first derivative. So let's take the first derivative of our perimeter. That's 2 plus 512 times, now the power rule, x to the minus 2 squared, to the minus 2. Okay, and so we can just do, oh, there's a negative there, so let's make that negative 512 over x squared. Right, so next we want the critical points. So that's where p prime is equal 0. And that will be 2 minus 512 over x squared is equal to 0, or when 2 is equal to 512 over x squared. And you can multiply both sides by x squared to get 2x squared is equal to 512, or x squared is equal to 256. And then if we square root both sides, we get plus minus 16. Another critical point is where p prime does not exist. And this occurs when my denominator over here is 0. So when x squared is equal to 0, or when x equals 0. All right, let me put this maybe over here. So we want to find which is a minima. So let's put these on a sign chart, -16, 0, and +16. Those are the three values I got between these two types of critical points. So let's see, I want to maybe test -17, -1, +1, and +17. I think those would be good test points. So again, we're going to plug those into P prime. So P prime of -17, our P prime is over here. So that's 2 minus 512 over -17 squared. So if you do that, I get a positive number. Just plug that in a calculator and see that you get a positive number. When I plug in P prime of -1, I get 2 minus 512 over -1 squared, which will give me a negative number. You can verify that yourself. And then P prime of 1, it's same kind of deal, just because of that square in the denominator. So it will still give me a negative. And then P prime of 17, that will give me a positive number. So just verify, oops, sorry about that. Just verify it on your own that this is the sign chart you get. And so if we look, this means that I have a maxima at -16. My F is decreasing, then increasing around 16, and then no extrema at 0. And so +16 is our answer. Now, of course, you could also use the logic that if x were equal to -16, that means that my side is -16, which makes no sense in terms of area and perimeter. So if you'd like that kind of logic as well, you can also do x equals 0. Then you wouldn't have any area, right? You would have a equals 0 times this y, which would not give me 256. But it's always good to check with the sign chart that we get this kind of behavior. All right, so x is equal to 16. That will minimize my perimeter, but are we done? That is no, right? Because they want the dimensions, so they want a y value. So I'm going to return to our relationship or equation here to find what my y is. So 256 over 16. So happens that my y is also 16. So that really means that when my rectangle is actually a square, then my perimeter will be minimized. Let's do one more with a rectangle. Again, I'm just going to use x and y. So now we have a perimeter of 128. So my P is equal to 128. And perimeter is 2x plus 2y. And we want to maximize area now. Maximize area, which is x times y. Now it's the product of the two for this area. So again, I'm going to take the derivative of a, but before I do that, a needs to be in terms of one variable. So let's use our perimeter equation to solve for y. So if I move 2x to the other side, and then divide both sides by 2, I get 64 minus x is equal to y. So let's plug that into my area, and I get 64 minus x times x, distribute it in, and that's what I got for my area function in terms of x. So let's go ahead and take the derivative of a prime, or the derivative of a, and that will give me 64 minus 2x. It will never not be defined, right, because it is a line, but when it equals 60 or 0, that will be when 64 minus 2 is equal to 0, so 2 is equal to 64, where x is equal to 32. All right, so let's verify that 32 is a maxima for area, we will test the point 0 and 33, plug them into my A prime. So A prime, that gives me 64 minus 2 times 0, which gives me a positive number, positive 64. Then if I plug in 33, I get 64 minus 2 times 33. So that will be 64 minus 66, which will be a negative number. So that means around 32, we're increasing before, decreasing after. So 32 is a local max. So we definitely have x equals 32. And to finish, we need the other side length, y. All right, so that was given by this relationship. So y is equal to 64 minus x, which we found to be 32. So y is also 32. So our side lengths are 32 and 32. Again, we have a square. All right, let's do 2 application problems using our price, demand, and cost equations. So, and it's a little confusing because they use P, lowercase p for your price demand, and then later we'll see profit with a capital P. So I'll try to keep them straight for you. But anyway, for this one, we want to know what maximizes the weekly revenue, and then what is the value. So let's break it down step by step. Okay, so my revenue, I'm going to denote as R of X. This is going to be my X times my price demand function. So X times all of this, 600 minus 0.1x. So we can distribute that through 600x minus 0.1x squared. And so now let's find r prime of x. That will be 600 minus 0.1 times 2x, or 600 minus 0.2x. All right, so will this ever not be defined? No. Right, it's still a line. So let's solve for where it's equal to 0. So that's this equation, and that occurs when 0.2x is equal to 600, or when x is equal to 3,000. So now we have to verify that x equals 3,000 is a maxima. So let's make a quick sign chart. We can test the point 0 and 3,001. Right, and then plug that into my r prime. So r prime of 0, 600 minus 0.2 times 0, that will give me a positive number. And then r prime of 3,000, you can plug that in, 3,001. Okay, you can use a calculator for this, it's okay. 3,001 will give me a -2, I believe. But again, it will be a negative number. You're really only focusing on the sign here. So then that means that around 3,000, we're increasing before, decreasing after. So 3,000 is a maxima. So 3,000 is the number of phones that we produce. So that's 3,000. All right. And now we want to know the price. So we can use our price function that was given here. So the price is equal to 600 minus 0.1 times 3,000. And you can plug this into your calculator, and I got 300. Right. And then the very last question to this part is the maximum weekly revenue. So this is asking, what is R of 3,000? What is the revenue when x is equal to 3,000? So we want to plug 3,000 into this equation. So 600 times 3,000 minus 0.1 times 3,000 squared. So again, you can definitely use your calculator here. This should give you 900,000. And so that's this answer over here. So now B is asking about profit. What maximizes weekly profit? So recall that profit, and I'm going to denote it with this capital P of X. Our profit is our revenue minus cost, minus our cost, which is also given. So my revenue, which is directly above, that's 600x minus 0.1x squared, minus my cost function. So this is given in the prompt, 1500 plus 135x. So you can combine it a little, multiply this negative through, and so we get 600 minus 135x, so that comes to 465, I believe, 465x minus 0.1x squared minus 1500, 15,000, right? Okay, yeah, 15,000. And so now we want the derivative of P. So that's just simply 465 minus 0.2x from our derivative rules. So now we want to know where is my P prime equal or not defined. Let's do that one first. Since my derivative is a line, it will always be defined, but it will equal 0 at some point. This occurs when 0.2x is equal to 465, or when x is equal to multiply or divide by 0.2. This gives me 2325. So we want to check that 2325 is a maximum. So let's test the points 0 and 2326. And this is a 5, by the way. All right, so let's plug those test points into my first derivative, 0. I'll make this a little smaller so we have room for the other questions. All right, so that will give me 465 minus 0.2. So this will give me a positive number. And then if we plug in 2326, that gives me, you can verify on your calculator again, but this will definitely give me a negative number. And so we have this increasing before, decreasing after. So 2325 is a maxima. And so they should produce 2325 phones each week at a price of, so again, kind of like the last part, we're going to plug it into our price function, price demand. So P is equal to 6. So this is lowercase p, not my profit. 600 minus 0.1 times this 2325. And so throw that in the calculator, and I got 367.50. So 367.50 for this part. And the last thing we want is the weekly profit. So now we want capital P, our profit, of 2326, and that's given here. Sorry, that's the derivative. That's given here. So let's plug in 2325, not 26, for x. So 465 times 2325 minus 0.1, 2325 squared minus 15,000. And if you put that in the calculator, I got 525,562.50. And that will be the answer here. All right. Let's do our final problem together. This one has a lot of parts, so let's see if we can work through it. It's kind of similar. All right. So maximum revenue, we are given cost and our price demand. So our revenue is equal to our profit. sorry, not profit, our price, x times our price demand function. So you got to keep those lowercase p and the uppercase p separate. I wish they used a different variable or letter, but anyway. So x times 200 minus x over 30, and this gives me 200x minus x squared over 30, or sometimes I like to write the coefficient as 1/30 times x squared. That's the same. So let's find r prime. That will just be 200 minus 2 over 30x, or 200 minus 1/15 x. Where is r prime not defined? Never, right? That's a line, but it is 0 when 200 minus 1 over 15x is equal to 0. So this is the same as saying 200 is equal to 1/15 x, and this gives me x equals, let's see, 3,000, I believe. All right, so let's see if 3,000 maximizes revenue. So r prime, let's test 0 and 3,001. So r prime of 0 gives me 200 minus 1 over 15 times 0. That's going to be a positive. R prime of 3,001, 200 minus 1/15 times 3,001. This will give me a negative. So we have the point increasing before 3,000, decreasing after, so 3,000 is in fact a maxima. And now we want to answer the question, so what's the maximum revenue? So now we're going to find our revenue of 3,000. So this is 200. This is given by this formula over here. So 200 times 3,000 minus 1 over 30, 3,000 squared. So plug that into the calculator and I got 300,000. Right, so the next part, we want to know the maximum profit. So remember that profit is, and this is capital P, profit's my revenue minus cost. So revenue, that's highlighted in yellow above. So that's my 200x minus 1/30 x squared minus my cost, which was given in the prompt. So that's 75,000 plus 50x, but I'm subtracting it, so it should be minus 50x. And then we can combine it just a little to make it slightly better when taking the derivative, which will be our next step. So now we want p prime of x, so this will be 150 minus 2 over 30x, or 150 minus 115x. So again, it's never not going to be defined, but it will equal 0 when 150 is equal to 1/15 x, or when x is equal to, let's see, what does that come out to? 2250, I believe. Okay, gotta check that 2250 is a maxima. 2250. So let's test 0 and 2251 in my p prime. So p prime of 0 is, let's see, it's 150 minus 1/15. Let me move our sign chart, just make it a little clearer what we're doing. All right, so let's find p prime of 0. That's 150 minus 1/15, 0, which is positive. And P prime of 2251, that will give me 150 minus 1/15 of 2251, which will give me a negative number. So again, we have increasing to decreasing about 2250. So the maximum profit is blank when we have 2250 sets, and when they're sold for blank each, that's given to us by our profit. Not profit, price. It's given to us by our price demand function, the small p. So of 2250, so 200 minus 2250 over 30. And this, I believe, gave me 125. So this will be, I'll write it in blue, 125. And then the maximum profit, this is our capital P now. Capital P, I guess, of 225, 220.50. And now we're going to plug it into this equation, our profit. So this will be 150 times 2250 minus 1 over 30, 2250 squared minus 75,000. So I get for this one to be 93,750. And so right here, this answer will be 93,750. Right, for this last part, we want to know what the maximum profit is, but when each set is taxed at $4 each. So this means that it will affect my cost. So I have to factor in a 4x into my costs. So we can combine our new cost function to be 75,054x. And we want to know about profit, which is revenue minus cost. So my profit function also changes. So the revenue is the same. That's the function we found in A. So 200x minus 130x squared. Right, and then we want to subtract off our new cost function, which we just found. So that's 75,000 minus 54x. And we can simplify just a little bit to make the derivative slightly easier. Combine those 200x minus 54x into 146x minus 130x squared minus 75,000. So let's take the derivative. We get 146 minus 115x. So notice that P prime is not going to be not defined anywhere, but it will equal to 0, and this will occur when 146 is equal to 1/15x, or when my x is 2190. So let's verify if 2190 is a maxima. So let's plug in 0, 2191 into our P prime. So P prime of 0, we get 146 minus 1 over 15 times 0. That's going to give me a positive number. P prime of 2191, that will give me a negative number, which is what we would expect, because then that means that we have a maximum at 2190, right? Increasing then decreasing. So our answer for blank sets is 2191, or 90, right? 91 was our test point. So 2190 sets at what rate for each? So that will be determined by our price, our lowercase p, price demand. So let's find the price demand when it is 2190. So if we plug that in, 200 minus 2190 over 30, This will give me 127, so this is the price per set. So 21 or 127, sorry. And then our very last piece is what's this maximum profit when we sell 21.90 at 127 each. So now we want capital P, which I'm kind of making bolded, of 21.90, and using our P, our profit function that we found here based on our new cost function. So 146, plug in 21.90 wherever our C and X, minus 1 over 30, 21.90 squared, and then subtract out that 75,000. And if you plug that into a calculator, I got 84,870. And then that will be your answer to this one. So I know there's a lot crammed here, but I'll write out these solutions as well as the one to the previous question as well, just so it's a little clearer, and I'll link them in the description as well on Canvas. All right, well, that sums up 11.6, chapter 11, and pretty much this whole semester. So now you just got to finish strong with the project, the final project, and good luck with the rest of your studies, and I hope to see you again.